So the final topic that we're going to cover today is how do you interpret your R values? So when you look at R values, in almost all the examples that I've given and that you see in textbooks, there's very strong correlations, right? So you see an R like this, where it's just a very tight correlation. It's very strong. It's really nice. But in fact, you can have weak correlations that are very important, particularly in ecology. So, and why we'll get to in a second. So if you look at a weak correlation, look at page 130 of the textbook, and you can look at the difference between an R of 0 and an R of 0.3. And if you just look at them, you cannot tell the difference. They're incredibly difficult to tell. The human eye is just very bad at finding weak correlations. They look like a cloud of points, pretty much. And it's just that when you're talking about 0.3, right, the cloud just gets a little denser down there than it is in other places, right, if you have a negative relationship. But it's really hard to discern that pattern. But it can be really important, right, particularly in ecology, where there are a lot of things that we cannot measure. So a great example, and this is what we'll end on. So a great example is that I had an advisor who published a paper on horn size in African buffalo and how they're related to parasites. Now, if you think that African buffalo are these huge, big, ferocious, nasty animals, and they have horns that look like this, they're kind of shaped like this on the males, and the females are shaped kind of like this, and they're big bruisers, nasty beasts. Very cool, but very nasty. And what she looked at females, and she looked at horn size and as it relates to parasites. So now, what she did is that she captured about 200 buffalo, and she measured all sorts of stuff. She had their age. So here are the variables that she had. She had their age. She had horn size. And she had parasites that she measured by fecal egg counts. Okay, so what she found is that if you could correct, she measured other things as well, but these are the most important for our purposes here, right, is that what she found is that if you correct for age, once you correct for age, we can find his number of parasites actually has pretty reasonably strong effect on horn size. But if she had an R value between, so if you did a graph, and you put parasites here, which was really an egg count, really a fecal egg count, and you'll get horn size here, and this is about what it looked like. It was all over the place. It was a mess, but you had an R value of 0.3. This got published in a really good journal. Now you can see an R value of 0.03, you can say, well, that's really insignificant. That doesn't have any effect almost on horn size at all. Right? That R squared is 0.09. That's really weak. There's less than 10% of the variation here can be explained by parasites. But think about this. What kind of things control horn size other than age? So they already had controlled for sex. So what things control for horn size other than age? So, well, maybe whether you grew up, whether you were a juvenile in really good years where there was lots of food around versus when you're a drought. That's going to have a big effect, right, on how big you can grow your horns. Your genetics are going to have an effect. Whether you got a lot of milk from your mother when you were a calf has a big effect, right? So there are so many things that affect horn size that are not parasites. And even if you think about parasites, was that they only measured parasites that they had that day, right? So parasites that they had that day itself had no causal relationship to horn size, right? Like if parasites have a relationship with horn size, it would be parasites that you had in the past, but they had no way to measure parasites in the past. They just had ways to measure parasites today. So the point is that you would expect to see almost no relationship. In fact, you would expect to see no relationship. And if at best, you would expect to see a very weak relationship. So the fact that they saw a relationship at all, a weak one, means that this actually parasites must have a pretty strong effect because there's so many things that affect horn size. So what's my point? My point is, we always look at these nice, strong correlations and say, oh, these are things that are important. But in fact, weak correlations can also be important. You just have to interpret your results. We have to think if you have a variable that you think is actually going to have no correlation at all, or at best a very weak correlation. If you find a very weak correlation, that is the best case scenario. That means that it actually does have a strong effect despite everything else that's happening and all the glorious, messy ecology that's out there. So the greater take-home message here is that correlation is a tool that you can use to describe relationships between two variables, but only you can describe them and interpret them and decide whether it's important or unimportant. And so with that, we're going to end, and then in the next lesson, we're going to cover something completely different. We're going to move past correlation. Instead, we're going to move on to how you generate data and how you do sampling, how you actually generate these points.